basis of froth flotation is the difference in wettabilities of different minerals. Particles range from those that are easily wettable by water, hydrophilic, to those that are water repellent, hydrophobic. If a mixture of hydrophobic and hydrophilic particles are suspended in water and air is bubbled through the suspension, then the hydrophobic particles will tend to attach to the air bubbles and float to the surface as shown in Figure 1. The froth layer that forms on the surface will then be heavily loaded with the hydrophobic mineral and can be removed as separated product. The hydrophilic particles will have much less tendency to attach to air bubbles, and so it will remain in suspension and be flushed away, according to Whelan and Brown, 1956. Particles can either be naturally hydrophobic or the hydrophobicity can be induced by chemical treatments. Naturally, hydrophobic materials include hydrocarbons and nonpolar solids such as elemental sulfur. Attachment of the bubbles to the surface is determined by the interfacial energies between the solid, liquid, and gas phases. This is determined by the Young-Duper equation. Young-Duper equation: surface energy of the liquid-vapor interface times cosine theta, or the contact angle, equals surface energy of the solid-vapor interface minus surface energy of the liquid-vapor interface. The contact angle is the angle formed at the junction between vapor, solid, and liquid phases. Figure 2 illustrates the contact angle between the air bubble and the solid surface immersed in liquid. In performance calculations, methods that are useful for examining froth flotation processes include ratio of concentration, percent metal recovery, percent metal loss, percent weight recovery, and enrichment ratio. Ratio of concentration is the weight of the feed relative to the weight of the concentrate. The ratio of concentration is F over C, where F is the total weight of the feed and C is the total weight of the concentrate. One limitation with this calculation is that it uses the weights of the feed and concentrate. While this data is available in laboratory experiments, in the plant, it is likely that the ore is not weighed and only assays will be available. However, it is possible to express the ratio of concentration in terms of ore assays, starting with the mass balance equation and the definition of the ratio of concentration. The ratio of concentration, F over C, is equal to the difference of the assays of concentrate and tailings all over the difference between the assays of the feed and tailings. Percent metal recovery is the percentage of the metal in the original feed that is recovered in the concentrate. This can be calculated using weights and assays, or the percent metal recovery can be calculated from assays alone. The percent metal loss is the opposite of the percent metal recovery and represents the material loss to the tailings. Percent metal loss is equal to 100 minus the percent metal recovery. Percent weight recovery is essentially the inverse of the ratio of concentration. Enrichment ratio is calculated directly from assays as the assays of concentrate over the assays of feed. Weights are not involved in the calculation.